In this work, my co-authors and I look at the lifetimes of molecular star-forming regions across the different hierarchical levels of the interstellar medium. It has been known for many years that the gas of the interstellar medium is fractal and hierarchical in nature. This fractal structure is described by scaling relations consistent with a compressible and supersonic turbulent cascade of energy from large to small scales. We also know that the majority of stars are formed in molecular gas. On average, gas that is dense enough to be shielded from atomization by the UV radiation field is also shielded from heating by this same radiation field, so can cool down to temperatures low enough for collapse and star formation to occur. On each spatial scale, regions of high molecular gas density are found to be organized into discrete objects, which we call molecular clouds. As telescopes have become more powerful, molecular clouds have been observed not just inside the Milky Way, but across a wide range of other galaxies. Star-forming regions have even been observed in galaxies at high redshift. These observations of galaxies at different distances resolve different levels of the interstellar medium hierarchy. To examine molecular cloud properties across this large range of spatial resolutions, we identify clouds in simulated galaxies at 6 parsec resolution, and then compare these to clouds in maps of degraded spatial resolution down to half a kiloparsec. We track the molecular cloud evolution over time to produce a cloud evolution network. Each of the circles on the left represents a molecular cloud at a particular simulation time, and each white line, as well as each different color, represents the time-dependent evolution of the cloud. In each network, we can see cloud mergers occurring, and we can see where a single cloud splits into multiple parts. In particular, the molecular cloud lifetime is interesting, because this gives an upper limit on the timescale for star formation on a particular level of the hierarchical interstellar medium. The complex structure of the network means that we have to be careful not to double count the clouds as we calculate their lifetimes. We perform a Monte Carlo walk through the cloud evolution network and iterate this until the distribution of cloud lifetimes converges. By compiling the Monte Carlo realizations, we can calculate a half-life for the clouds at each spatial resolution. This is equivalent to the mean timescale for cloud destruction. We find that the mean cloud lifetime varies with the size of identified clouds across the range of spatial resolutions and can be divided into two distinct regimes. The lifetimes of clouds with scales larger than the gas disk scale height are destroyed on the turbulent crossing time of the gas disk, while below the gas disk scale height they obey a power law. At low spatial resolutions, the star formation rates of identified clouds are low and relatively constant. The clouds are gravitationally unbound on average. These regions show no evidence of being destroyed by feedback. The timescale for star formation is given by the turbulent crossing time, consistent with clouds that are vertically confined by the gas disk. However, if clouds are resolved on scales smaller than the gas disk scale height, their average evolution shows clear evidence of collapse, then an increase in star formation, then subsequent unbinding by stellar feedback. Collapsing clouds with longer lifetimes are more likely to be observed at smaller sizes, accounting for the form of the power law. In summary, it appears that the spatial resolution needs to be smaller than the gas disk's scale height in order to resolve the cycle of collapse, star formation, and dispersal associated with pound clouds.